Again, good day. So today for now we will be discussing A202. This is one of the questions in our feedback and control system lab assessments. This is the finals. So the question for LA202 is a fighter aircraft has the transfer function of, as you can see here, it's negative 10 times s plus 1, s plus 0.01, this is multiplied by s plus 1, over s squared plus 2s plus 2, multiplied by s squared plus 0.02 plus 0.0101, where the theta dot is the pitch rate, and in radians per second is the deflection in radians. A pair of complex poles represented in the Pugoid mode, while the other pairs represent the short period mode. The Pugoid mode has a natural frequency of 0.1 radian per second, while the short period mode has a natural frequency of 1.41 radians per second. The block diagram for the system with feedback and cascaded compensation is shown below. As you can see here, this is the system that is required for an answer. This is the lead compensator, which is GS. Actuator is negative 10 over S plus 10. And the aircraft is negative 10 S plus 1 times S plus 0.01 over the given S squared plus 2S plus 2 times S squared plus 0.02 S plus 0.0101. Okay, so the first question is, which poles of the aircraft transfer function corresponds to Pugoid mode, and which poles correspond to short period mode? Discuss how were you able to determine this. Plot the open loop step response of the aircraft dynamics and explain how the step response exhibits non-minimum phase behavior. As you can see here, I had managed to use the transfer function given for the GS, which is negative 10 times s plus 1 times s plus 0.01 over s squared plus 2 times s plus 2 times s squared plus 0.02 s times s 0.01, and the feedback G1 and the P step T. Well, if I will show you how I managed to get this by going to our MATLAB Online. I'm using MATLAB Online as I had shown earlier for the other questions. Okay. Plugging it in so that we can see for ourselves what poles and zeros that we could see in this script. This is the feedback. Waiting for it, and you can see the figure here. This is the poles, this is the zeros, and these are the poles. Okay, to make it much better for us to see. You could also type grid here if you want, instead of clicking the grid. Okay, so showing you the step response of the system. The figure will change since I hadn't saved it. So this is the step response. As you can see here, this is what the feedback transfer function has shown for the step response. Okay. So as you can see here, it has shown you the step response. So going back, as mentioned, we had to plot the step response of the zeros and poles. We also need to see where the Pugoid mode and the short mode is. So using this function for the system, I will just copy and paste it since I had done it earlier. I'm just showing you how I did it and discussing you the following script for it. Okay. I will be using Bode plot for us to know which part of the poles is the pugil and the short mode. Okay. As you can see, this Bode diagram is shown here, and I had managed to let you know what type of what is the pugoid mode and the short mode is. As you can see, here is the pugoid mode. The pugoid mode is here. This is the diagram for my pugoid mode, while the short mode is here. As you can see here, this is the short mode. Okay. This is the pugoid mode, at least. So the next question is, let the compensator to be in a pure gain at this point. The value of the gain of the pugoid closed loop pole, which has a damping ratio that corresponds to the 10% overshoot. Again, note that we will be using a 10% overshoot. With this gain, characterize the pitch rate to a step command, including the steady state error. Given the 10% overshoot, we will find the gain margin by the root locus. Okay, so using again the transfer function, feedback, and the loop locus, we will be showing a margin of t. So for this question, the root locus is for the gain is infinite, as you can see here. If I will plug all of the questions here, or the t feedback, since we are still using the same function, I will just plug it instantly here. It will overwrite all of the script functions, and it will show you the root locus. And for the margin, showing you the margin here. So if we so you can see there's a value, so it's 1.9792 plus E03, but for our given, it's an infinite value, since the given for it shows that it is infinite for this matter. So letter C is let the lead compensator be GS KZ plus ZC. Design the lead compensator so that the pitch rate setting time is half while maintaining the damping ratio of the pugoid closed loop pole parts in part B. Verify the compensated system transfer response and steady state error performances. I had used this equation: ln times overshoot over 100%, while over pi squared plus ln cube, and OS is overshoot over 100. Since the overshoot is 10%, I had plug in the overshoot equation, giving me a calculation of 0.910281. So using this formula right here, theta is equal to cos minus cos, our cos 0.9. So this will be showing 25.841937726. Okay, so this will be the compensated system for the transfer response and steady state response performances. That's all for my questions. Thank you so much for your time and listening to my discussion. You have a good day. Thank you.